Okay, so now it will be again me talking. And I'm very excited to be responsible for some kind of a technical stuff. Because actually I'm a disaster person with all of related with technical stuff. We have listened to a perfect talk about OpenCravat, what it is, or like a variant of it. And okay, to make things simple, let's do a small hello world example and starting analyzing and learn how to analyze your own genome, your own VCF file using OpenCravat or QUAR. Let's begin with some simple example from Anton's genome. And it will be related to pharmacogenetics. I have already sent you a link to OpenCravat server. You can just open it, and until while I am talking, you can try to log in. And I hope everything goes well with it. You can use antonkolaga@gmail.com as a login and a password RCBI 2022. So if something will goes wrong with it, we have some another variant how we can work together. But please, first of all, try this one, and I hope everything will go well with it. Okay, so while you're trying to do that, I will tell a little bit about pharmacogenetics. Pharmacogenetics actually is an important thing in the personal medicine, and it is related to choosing the appropriate drug for use, the doses and forms of some drugs, and also to estimate your personal risk related to taking this appropriate medicine. Your genes are coding the enzymes which participate in drug metabolism. So you can be a fast metabolizer, like an intermediate one, or a slow one. And all of these affect the dosage of the prescription you have to take for this medicine, and also the adverse effects. So what you see in the prescription list in the instruction to the drug is usually like an intermediate variant. You can need it a higher dose or a lower dose of it. And so we will look for it. Okay, I will just, how can I just look into the chart whether everything is fine? Got it. Beginners ourselves. We will firstly work with Anton's genome and with several clinical cases which are already uploaded. And after that, you can switch to work with your own genome. Okay. Okay, so hope everyone has already logged in. Yeah. Is everything fine? Is someone having problems? Okay. I see no one telling that have problems, so probably it's just fine. Okay, so I'll just log in myself and then we continue. So if you have done it successfully, you can see something like that. There are several genomes we have already uploaded for you. So it, in that case, it would be faster. One of them is Anton's genome. Some of them are for our clinical cases, and some of them to show you. How actually, I will briefly tell how actually you can upload your own genome. if you haven't done it already, you will be able to do it after our workshop, just taking your cup of tea and working with OpenCravat. So first of all, you have to choose the assembled version of your genome, and that is important. Usually the company that gives you your raw data, you can find this information there, which assembled version of your genome was used. If you will choose the wrong one, you may gain wrong results. Also, there are some converters. So if you have 37 version of your genome and you want to work like with 38, you may convert it. Then you may choose add input file. With this link, you can just choose your VCF file from your computer. Okay, and later we will talk about different annotations. Okay, now we will just look to the Anton's genome. You can find Anton Kulaga VCF file. Here are some annotators which we choose are listed. And we are just choosing the results here. I suppose if a lot of people have downloaded, it may take some time to download the data. And if it will work too slow, we will have to switch to our server. Yeah, OpenCravat cannot display. Yeah, okay, I will start. Finally, it's got. OpenCravat viewer cannot display more than 100,000 variants. Use the filter tab to load at most 100,000 variants. That indeed is a problem, but we can solve it using some filters. Depending on the task we want to solve, we can use different filters, whether we want to find some pathogenic variants, some pharmacogenetic related variants, etc. And we can do it using the filter tabs. So there are several lines with filters. First is genes. Samples, it's used when you are working with oncological tissues, etc. It's not for personal genomics stuff, it's more for doctors. Generalist, if you're interested to find some variants in genes and you know these genes you want to look at, you can just type a list of genes or just put a list of genes here and you will be annotated with these genes. There are some filters which are automatical and you can use them as well, but usually we use Query Builder. It's a kind of a filter that you can choose like by yourself what you want to do. So you see here is a little plus, and actually the filters you can apply will depend which annotators you have chosen previously when you're uploading your genome. I will tell about it a little bit later. So now our task to make a short, where to put this window? Okay, a short hello world example, and we are going to find some genes which will affect the drug response related to pharmacogenomics. We have PharmGKB filter, and there is a PharmGKB annotator, which is related to this field. And when you're uploading your genome, if you're interested in finding something related to pharmacogenetics, you have to choose this one. Then You choose chemicals. It can chemicals which is already in the database of Pharmacogenomics and has data. Okay. Then we make plus. So if we want to annotate it not using just one annotator, we can use something to this filter. Also, there is a famous and important annotator, CleanVar. All of us are working with CleanVar. And there are several categories we can choose in CleanVar. And one of them is drugs. So you can find here drug response. Here you see pathogenic, benign, etc., drug response. Oh, we can do that. Hope it's not that fast. So we are choosing CleanVar, clinical significance, one off, and then we select just drug response. So we combine these two filters so it would be more reliable. If you combine them, here you can change and or. And that means that in using that filter, we will have variants which are annotated by Pharmacogenomics database and also exist in CleanVar database. So it makes it more reliable. And after we have chosen the filter we wanna work with, we can see how many variants we will get. We can't work with more than 100,000 variants. We can do it just clicking these small arrows, and it will show how many variants we will get using that filter. 78 variants. Okay, that is fine with us. We can annotate it using 78 variants. So actually, when you use filters, you can save this filter using this thing. Actually, it's not always working as for me, but sometimes it works. And also you can later use already chosen filters. We will do it when we will work with clinical cases. You can just upload the filter you have already saved, and it will be automatically built into your builder. Okay, so just apply filter. And then again, it's working. It's working that slowly, I think, because kind of plenty people have connected to the server. Usually it's a little bit fast, but it depends. But anyway, it's our own genome. It's not that long to know information about yourself. Okay, so now it has annotated. Then after it, you can choose. There are also two tabs, variant and gene. Usually I work with variant tab, so you can use just it. Oh, no, let's put this in. Okay. And it's kind of complicated for user. It looks not really user-friendly, but and when I first started working with OpenCravat, it was also complicated, but then you get used. And here you can find into the upper right corner some options. View table, view detail plane, view table plus detail plane. Usually I work with a table first, and it's a table which has gene variants according to your filter applied and genes which are thought to impact your own pharmacogenetic response. You can see the list of genes here. And actually, columns here, it depends on how many annotators you have uploaded for genome analysis. We have uploaded pretty much because we work with different stuff as Anton genome. Now we don't need all of them. We use just pharmacological ones. So we just pulling this thing until we find pharmGKB annotator. If you had more time, you can use just two annotators, and in that case, the amount of these columns will be much less. So here you can see the list of chemicals which you are supposed to have a changed response to. here you can type a chemical you want to search. Maybe you are taking something already or you're going to take something. We can try just statins. All of you know that statins are commonly used drugs for metabolic syndrome, for lipid metabolism, especially in later life, and also they're quite important and quite famous in longevity medicine. People take them, that stuff. So we can see here a list of drugs which are to be affected by your genotype. And you can see here simvastatin, rosuvastatin, etc. Yep. So we can choose one line and see what gene is that. For example, ApoA5 gene. So you can find here also the information which is important. VCF info is a little bit to the right from the PharmGKB column. VCF info, you can find zygosity. You know that you have 2 alleles of each gene variant. So, okay, exactly. So you can have both of them changed. So if you see here homozygous, like here, it means that you have alternative base for both alleles. If you are heterozygous, that means that one allele is alternative and one is reference. So after choosing some line of information, you can switch to view detail plane. Here you can see a lot of windows. It's widgets for annotators. We uploaded for genome analysis. You know, it depends how many you have chosen before the genome analysis. And usually, if you will choose just 2 annotators, there will be less. So we can see variant annotation, reference base is G, alternative base is A. So if you have homozygous variants, that means you are AA genotype carrier. So we also have ClinVar widget. You can go to the ClinVar link and see what information will give you ClinVar. So it says that this variant is indeed related to atorvastatin response. So, but we need to find PharmGKB widget, PharmGKB variant. Also, there is a GNOME ID widget. We will talk about it later. It shows the population frequency of this variant change total for different populations as well. So, but PharmGKB variant, tenofibrat is not wanted. Atorvastatin, tentative AA is associated with response to atorvastatin, rosuvastatin, and simvastatin in people with dyslipidemia. So it's our variant, and you know, alternative A, and we are homozygous. Anton is homozygous, so he's AA carrier, and the response is increased. Yeah, and here you see response, increased response to simvastatin. So yeah, probably, and here you can also see whether the data is significant. Yeah. So the efficacy is high and the response is increased. So maybe you have to think about decreasing the initial dose when you come to taking statins. But okay, it's not the only variant we have here. So our task is to analyze all of them. I hope we'll be able to create an annotator which will do it more user-friendly, and you can see all the variants like in one report, and you will be able to analyze it more easy. Okay, another one, heterozygous variant of a gene, ApoE gene. Yeah, you know, it's a gene very important for longevity. And then again, we are changing to view detail plane. Here we can see PharmGKB annotation. We have heterozygous variant, so CT variant, and then again we see that, for example, for fluvastatin, genotype CT is associated with increased response to fluvastatin as compared to other genomes. So yes, indeed, maybe according to already 2 variants, our response is increased. So we may think about lowering the dosage if we will need taking it. Okay, view table, again, view table. And we can have a look into the another variant, ABCG2G. So again, we are moving to VCF4. You can see that you are heterozygous, and you can see PharmGKB column. And also you see here the PharmGKB ID. You can also link this PharmGKB ID and find the additional information in PharmGKB database. Also, depending on how many annotators you use, you can find additional information in all of the columns. Yeah, for example, for PubMed, if you will click PubMed, you will get into links to PubMed associated with this gene. Okay, but we're interested in PharmGKB variant. Okay, just think here. No, usually it's faster. Okay, so it's loading. You can see it's quite a huge database related to pharmacogenetics, and you see everything related to your RSID, which were found in your genome in heterozygous variant. So you can see here all of the information, if there are some. For example, prescribing info. If there are existing guidelines published by some consortiums, you'll find them here, and you can see them, drug label annotation, according to these clinical guidelines. For example, increased plasma level of rosuvastatin have been observed in Asians. We recommend in starting dose, like depending on population, etc., etc., etc. Genetic polymorphism unknown that may lead to an increase in rosuvastatin exposure in patient is known. A reduction in the dosage is recommended. So indeed, according to already 3 genetic variants, you are responder to statins, so it will act on your lipid profile, but you most probably, you will need to decrease your dosage. And okay, you can switch to some different apps like clinical annotation, etc. And also you can download this PDF variant. So you can also see which evidence level for this polymorphism this data has, like 3 level of 4 level, etc. Okay. Okay, so evidence level means how you can be sure in this recommendation. So the highest evidence level means that, yeah, okay, a lot of people were engaged in the study and you can trust them. Okay, so let's continue. Let's continue. So it was kind of a hello world example. Now you get into some new experiences analyzing your VCF files. And now we can go then again to the OpenCravat. I hope you haven't closed it yet, and continue doing some stuff. I'll show just a few slides and then we will go back to the OpenCravat window. So if you are back to the OpenCravat server, you can see downloaded, pre-downloaded genomes. You can see annotations, which we can use. They are divided into several categories. Usually we work with variants, clinical relevance, allele frequency, genes, etc. Or you can choose just show all and then choose which you need. Okay, next one. Which annotators we usually use? So when you are first into the OpenCravat and you are just starting analyzing your genome, it's kind of complicated to choose the right set of annotators for analysis. We usually use this list of annotators, and we recommend it also for you if you will analyze your own genome. You will get the presentation afterwards, and you will be able to look at it. It's like CADD Exome. We use two sets of annotators. The first one is to see how damaging this variant is. And another one is to find out which information we can get about this substitution or SNP. So we use CADD Exome is a tool for scoring the deleteriousness of single nucleotide variants, as well as insertion deletion variants in the human genome. So it tells us how damaging this substitution is. Genome ID gene, I have already talked about it. It's about a population frequency. PubMed, PubMed articles related to a particular gene variant. LinGen, it's also an informational resource that defines the clinical relevance of genes and variants. ClinPred, it's prediction tool to identify disease-relevant variants. ClinVar, very big annotator, often used, contains an archive of reports of the relationships among human variation and phenotypes. MitoMap, it's for mitochondrial variants. It's not that popular, but we included it into the list. NCBI gene, it's gene descriptions from NCBI. OMIM, it's a catalog of human genes and genetic disorders. You need OMIM if you will analyze some variants related to some diseases. And then again, some annotators which will show us how damaging or tolerable this substitution is. It's REAC, Provine, Reveal, Shift prediction. So actually, we try to use just one of them, but none of them contains enough information to cover all the variants we can find in the genome. So we just combine different annotators for prediction of deleteriousness of some variants. So we will now move to the clinical cases analysis. It's real long clinical cases, and you will try to find a solution for one or another phenotype related to disorders. Clinical case number 1. You can see it's pre-downloaded. It's X13S adenine S1. It's a woman, 30 years old, so quite young. She has several complaints, progressive muscular dystrophy, whole genome. You can already, maybe I can already also push open result view, so it will be a little bit faster. It takes some time to. It takes some time to annotate. Okay. So she has a progressive muscular dystrophy. She did whole genome sequencing in 2017, but actually no genetic cause was found, and she got the diagnosis like myopathic syndrome of unknown origin. So she asked me a question, actually, is it worth redoing the genome or exome sequencing in Germany or some other country, anywhere, to find out whether it's genetically related disease and phenotype or no, or not. Some little overview of her complaints. Clinical picture, according to her words, she lived not in Odessa, so I haven't seen her even, so I just talked to her on the phone. The first symptoms of muscular fatigue appeared in childhood, so quite early, and it shows us actually that it's probably the genetical reason for this stuff. She also has frequent respiratory infections, etc. At the age of 12, the jaw began to get very tight, so it was difficult to chew from talking and chewing, and the fatigue increased and speech became slurred, and she also observed and increased difficulty in swallowing certain types of food. At the age of 20, weakness in the limbs appeared, so it was difficult to climb stairs. And previously, multiple sclerosis was suspected, then myasthenia gravis, and nothing was confirmed according to immunological testing. At the age of 23, the state of health was revealed. She observed weight loss by 7 kilos in 2 months. From this period, it became difficult to breathe. She also mentioned that she had some problems with food digestions. Mitochondrial myopathy, celiac disease were suspected, actually. That's why she asked us, because we were famous with mitochondrial diagnostic. A lot of disorders like immunological ones, gynecological, endocrinological, gastroenterological ones were excluded, and autoimmune disease were excluded as well. So now we will go to the OpenCravat again. Accepting the connection. Okay. Okay, just a second. It's a kind of slow with retrieving data, but while we are trying to retrieve it, you can. Okay, so then again, we see kind of a lot of gene variants to be analyzed at one time, and again, we have to use some filters. I forgot to do one stuff. I have to do it. I will send you now a filter, so it will make everything faster. After you download this file, okay, okay, here it is. I'm just sending it to you. No, I can't send it. No. Maybe I just can't share it. Okay, then we'll do it manually. I don't know. I don't know why, but okay, I can send you a link to the to my disk, and you can download the Okay, here you can see. Here you can see the folder with different files. We will use them during our talk, and you can now download pathogenic JSON. It's a filter for OpenCravat. Okay. So after we going to the filter tab, we have to choose some filter. We can apply already prepared filter for it, like pathogenic JSON. Okay, so you just choose this arrow, click on it, and then choose pathogenic JSON filter. You can download it from the link I have sent you. So while you are doing that, I will tell a little bit about this filter. So why have we choose it? We have chosen several filters which will show us the pathogenicity of the variants. It's like CADD Exome filter. Here we choose pH red, and it should be higher than 10 for this filter to estimate this variant as pathogenic. Here we choose SIFT filter, and here is easy. We're just choosing prediction, one-off, damaging. So it's quite easy, and you can always do it yourself. Like SIFT prediction has to be damaging when you're looking for some damaging variants. Reveal, it also shows us pathogenicity. Here we choose score and higher than 0.5. ClinVar, clinical significance, one-off, pathogenic. ClinPred score higher than 0.5. And we can combine filters, like when we want to choose or to end, we can group them. So we have grouped filters for pathogenicity estimation, and then filters for getting some data about these variants. It's like OMIM, entire ID has data, ClinVar ID has data, NCBI gene description has data. Okay, let's check what we get. Well, 9,000 variants. It's still kind of a lot of variants to analyze, at least now, to do it quickly. So which options we can use? If we are doctors, actually, we have to look to all of them. But for the first step, we can choose here and. When we choose here filters to end, what does it mean? It means that all these predictors, all these annotators, show this variant as a kind of pathogenic variant. Oh, and then again, we will see what happens. Yeah, we have just two variants. So, okay, that's not too long to check. We can apply this filter. So then again, wait a little bit until your variants will be analyzed. Okay, it's done. So we are choosing just variant tab and see what we get there. View table. So we have two genes, formed 1 and PN LIP gene, which were found to be pathogenic according to multiple prediction tools like CADD Exome, ClinPred, shift prediction, reveal prediction, and then we can just see what these variants are responsible for. So we can choose, for example, POMT1 gene and view detailed none. So we can see ClinVar. This variant is found to be pathogenic. ClinVar ID, we can use it a little bit later. So we see this gene is responsible for muscular dystrophy, type A, muscular dystrophy, dystrophinopathy, congenital with brain and eye abnormalities, type A. So type A. So it kind of correlated with our, I can't see the amine here. Maybe I haven't downloaded it like, okay, it's kind of correlate with our clinical symptoms. So we can just put here. And go to the ClinVar. So you see this variant is pathogenic variant. And you can also see which submitter has downloaded the genome where it was found as pathogenic. You see that CADD Center of Human Genetic Tübingen has downloaded, submitted that this variant is pathogenic, and it happened in 2021. So it's happened, this variant has been shown to be pathogenic a little bit later than this, than the time of which this woman has her genome sequenced to be done. So we can briefly go again to the presentation. So what we do. So when we have too many variants, like we got there like 9,000 variants to analyze at the first time, too much to analyze fast, we can go by several ways. First, we can do like we have done, change OR to AND and see the most relevant genetical variants estimated as pathogenic by all predictors and check others. Or, and which is done most frequently, we can add gene list to the filter according to the problem, AJ muscle weakness. So for this clinical case, we tried the second variant and it worked for us since it was not our task. It's what we have done. Was not our task to get an exact diagnosis. The question was just whether she should to resequence her genome, and actually he should, because the quality of the coverage was not that good. So we have found two genes according to our filters, PNLP deficiency of pancreatic lipase. If we can go to the second one, we will find it. So as you remember, she was complained about some gastrointestinal disorders. So the absorption of fats may be impaired. And POMP1 gene is responsible for muscular dystrophy, for dystonia, and defects in this gene are a cause of Warburg syndrome and limb-girdle muscular dystrophy. So exactly as the complaints that she has. So it's what we see when we go to the ClinVar. And then we can slowly go to the clinical case number 2. It's 94306. You can open the result viewer. I will close all the other tabs. Or maybe in that case, it will be a little bit faster. Okay, so until it is downloading, we can talk a little bit. Okay, let's do it. Okay, clinical case number 2. It was a girl. It is a girl. It is a girl just 4 years old. Which indications she got? She has short stature with skeletal dysplasia and delayed psychomotor development, delayed growth. She's like a little one, very nice, but very little. Low weight gain, and she's not talking. She has delayed speech and language development. But actually, she has some face features which are not usual for like normal genomic ones, muscular hypotonia, etc. And she was providing a test called exome sequencing by Illumina, by genetic laboratory in Germany. So until we see the results of the sequencing, we can try to find out the reason for this phenotype by ourselves. Okay, I will also send you. Okay, so it's still working. OpenCravat still working. Still haven't analyzed. So I'll just briefly look. Okay, I have sent you a link to the folder. Don't miss it. You will also need it for some more things to download from it. I think the last one is the slowest one. Okay, while it's going, you can download from the link I have sent you the file with list of genes related to intellectual disability. See this file, intellectual, or maybe you don't see this file, intellectual disability file. You can just download it and then, or just open it and then copy paste the genes from there to the field. Okay, it's still analyzing. After it have to be faster, I hope. I don't know, maybe a lot of people get connected, so that's why it's a little bit slowing it down. I don't know how it works at your computers. I think it's also kind of slow. Okay. Okay, so we can just move to the presentation and see what we will do next after the analysis. Maybe I have just to do it one more time. Maybe it will be faster. I don't know. Okay. After it will be downloaded, what are we going to do? Then again, we will go to the filter tab and choose filters, or we will use actually the filter you have already downloaded, the pathogenic one filter that we have already applied. Actually, it's quite universal filter, and you can use it quite broadly when things come to some pathogenic variants analyzing. But we get kind of a lot of variants according to that filter, and I will go further and tell that in this case, changing or to end and analyze by all clinical significant predictions didn't work, so we'll just use the list of genes which you can download or just copy paste, and we will put them. These genes are related to the pathology, so it's like intellectual disability list of genes. We will put the list of genes to the filter tab, and we will analyze just these genes. It just doesn't wanna work. Okay, I will try to do it on the server. Maybe here it will be faster, so I can just briefly show you how we will work with it. And after it will be downloaded on your computers, you'll be able to do it yourself. Oh, okay, I think here it, okay. Yeah. Here it's okay, and here it's still analyzing. Okay, I will move to our server to show you fastly. So we are uploading the filter pathogenic with name pathogenic JSON. So, and trying to apply this filter and see that then again we have quite a plenty of results, more than 6,000 results. Actually, we can analyze all of them or just try to use a set of genes. Oh, here I'm just copy paste the genes from the list. Actually, this list of genes they are easily found, and they exist for different pathologies like cardiovascular, neurological, etc. And all of the commercial laboratories, they analyzed your genome according to the phenotype using gen lists. Firstly, and then if nothing is found, they just switch to the to broaden the search. Okay, 160 variants, so we can retrieve our data. Switch to the variant tab. So still kind of a lot of genes that we have to analyze. And actually, if we are doctors, we will have to take our time and analyze all of them. But now we can do some interesting things. You remember I have talked about the CADD Exome. It's a potential tool for pathogenicity prediction, and you can just make your list of genes in accordance to CADD Exome score. It's quite easy, and you can start analyzing from the genes which are thought to be most pathogenic according to the CADD Exome score. So you can see here that the first one from genes which we can use for neurological diseases, intellectual disabilities, abnormalities, is SRCAP gene, and its score is 39. It's quite a high score, so we can find the additional information we will need for the analysis. If we are doctors here, the most important one of the most important is zygosity. So some of the diseases are affects you just when they are in homozygous form. So they are recessive diseases, and some of diseases affect the phenotype even when one allele of the gene is changed. even in heterozygous type. Okay, so we can switch into the detail analysis. View detail plane here. And see ClinVar analysis and AMIM analysis, etc. So ClinVar, it's thought to be pathogenic. A ClinVar ID, we will move to that. It's floating harbor syndrome. What does it mean? We will find out from AMIM. I still don't see the AMIM widget. That is strange. Usually it's here. But okay, then we can go just to the ClinVar ID and check it, and go to the AMIM ID and also check whether it's related to our syndrome phenotype. So you see ClinVar ID, it's sort of pathogenic, floating harbor syndrome, autosomal dominant inheritance. It means that even one broken copy of this gene, like we have in the patient, is enough to develop the phenotype of the disease. Still, here it's still working. I don't know. I hope at your computers it's a little bit faster. So let's move to the presentation again. So what we have done, we have applied a set of genes related to our phenotype, then applied the filter, which we have already uploaded previously, got some variants. Then we made sorting according to CADD Exome pH-red. What does it mean? The last column of the provided files is pH-red, like it's the value greater of 10 indicates that these are predicted to be one of the 10% most deleterious substitutions that you can do to the human genome. So and the score greater or equal 20 indicates 1% of most deleterious, and so on. And we got 39, it's a higher score. So then we go to the ClinVar widget and see that it's pathogenic. Sequence ontology is top gained. A sequence variant whereby at least one base of a codon is changed, resulting in a premature stop codon. So it's quite deleterious thing. ClinVar say that floating harbor syndrome, Provine, Reveal, and Sift has no data. So that's why we couldn't just check or to end like we made previously and check all of the pathogenicity scores. OMIM, it's ID for AMIM, zygosity, heterozygous. So if you go to the AMIM data, you can find it's even heterozygous mutations. It's exactly what we saw in the genome of this patient. In this gene also cause development and delay, hypotonia, muscular skeletal defects, and behavioral abnormalities. It's a rare genetic disorder which is characterized by short stature, delayed bone age, delayed speech development, and typical facial features. Yeah, so it's exactly what we were looking for. It's exactly in accordance to a phenotype of our patient. And when we go to the ClinVar, we see that interpretation is pathogenic and autosomal dominant inheritance. What if we will look it from 6,000 variants, if we wouldn't apply the gen list? We will anyway find this variant, so we will have to check from the very up all of the genes, which pathologies they are related to, how do they inherit it, whether they are in accordance to our phenotype or not, etc. And then again, on the 1, 2, 3, 4, 5, 6, 7th place, you will find the gene which are most likely responsible for our phenotype and this disease. So we'll be right. It's what we got from the CADD report. So exactly, it's a commercial laboratory which providing genetical testing for the diseases. And they also found they detected a pathogenic variant in gene SRCAP, which is a causative of floating harbor syndrome in your patient. So you see that I can tell it's quite of a complicated and it's a high responsibility to work with patient genomes. But everything is possible, and I know that when you will work with your own genome, it's not such a responsibility, so you will not look for some genetical abnormalities. Most likely it's just some variants of some traits which are not that pathogenic. So the next step of our work is to work with our own VCF files. Yeah, I will briefly stop it and look. Okay. I don't know whether it will be possible to work with our own genomes, whether OpenCravat will allow us to do it now, but if you will have questions with working with your own VCF files with OpenCravat, you can just ask it directly and I will help to choose a set of filters, a set of annotators, etc. Okay, so then again, let's move to the presentation. Yep. So let's briefly check some things, some common things which can be analyzed in your genome. Or in my case, I will analyze in Anton's genome because I haven't already get the results of my own genome sequences. It's methylation, folate metabolism, need of supplementation. It's a very popular thing. Neurotransmitters, cDNA3, smoking adduction, and everything. You want to check afterwards if you will be able to do that. So methylation, what is that? What's the methylation genes, folate metabolism genes? If you're related to kind of longevity, personal medicine, you can't hear about that. It's a very important cycle in our organism, which makes possible some chemical changes, and it affects, it includes methionine metabolism, methionine to homocysteine transversion. And if this cycle, if these methylation processes don't work appropriately, it can lead to several pathologies, like you know that appropriate gene methylations allow silence some genes. For example, oncogenes are silenced, retrotransposons genes are silenced, and it's a problem when with age, methylation kind of changes, and some retrotransposons became active, and it affects our genome stability, and also and actually it's one of the reasons of aging. But then again, about methylation, and let's go back to it. Appropriate work of methylation cycle enables appropriate toxins clearance, glutathione system work, mitochondria appropriate functioning, because of during that cycle also glutathione is formed, etc. And this cycle is really dependent on vitamin of B group availability. Yeah, so you obtain them from our diet, like B12, B9, folate, B6, etc. But some people have gene variants which makes availability of these vitamins like lower. So they are transformed to their active forms, in which they are going to the metabolic cycles in a less extent than like people with different genetic variants. And actually, it's corrected quite easily. If you know your gen variants, what is affected, you can use some kind of supplementation. Usually, if you have changes in MTHFR gene, and okay, gen changes is not a prescription for taking something, but it's a kind of an alert that you have to, maybe you have to check your blood level for these vitamins, and combining such results, make a decision with your health practitioner about supplementing or not supplementing some vitamins, or maybe increasing them in your diet, etc. So MTHFR gene, it's benign usually. MTHFR, it's cobalamin, B12, CBS gene. It's very interesting gene. It depends on B6 vitamin, and actually the working of this cystathionine beta synthase, it gains it is related to serum metabolism, which is also very important for mitochondria functioning, etc., and the BHMT gene to beta. So if you have already your genome uploaded, or you are planning to do it a little bit later after our workshop, you can use it with filters I have shown that we usually use, annotators, and filters as well. And we can just check these genes. So I will try to work on Anton's genome and hope that OpenCravat will work now. So I'll just open the result viewer. Yeah, okay, it works. Variant, okay. Then again, we have too much variance and we need to apply filter. So we can upload our favorite genomic JSON filter and it will show whether some kind of deleterious variants we have. I will copy paste the genes from the presentation. Okay. Or you can just type them like MTHFR, MTR. I will send you a list of genes so you can also use them for analysis. Okay, and we will see what we get. Okay, we will see how many variants we will have. Okay, just 3 variants. It's nice. Apply filter. Okay. Variant tab, view table. What we see? Some genes, MTHFR gene, just MTR, and again MTR gene. Okay, we can go to the right and see different annotators, like what tells us. Linvar, methylcobalamin, it's methylcobalamin metabolism is affected, etc., etc., etc. From GKB. Okay, shift prediction, damaging to related damaging. Okay, but when we see it, we should definitely see the zygosity of this gene. When they're heterozygous, it's not that that much affected by your vitamin metabolism, like when it's homozygous. So then we can see, for example, we are choosing the gene, we're analyzing MTR gene and show the detailed plan and see what this gene is responsible for. You can see methionine biosynthesis have been identified like a cause of methylcobalamin deficiency. Yeah, so if you have some variants of this gene and you see it can be pathogenic, you can choose it by, you can check it by different annotators and see what do they say, methylcobalamin deficiency. Also analyze some papers from PubMed and find out that, okay, I need some additional supplementation of vitamins. For example, if we are talking about these genes. Okay, let's go again to the presentation. Okay, it's what we have gained. So we have found several polymorphisms estimated as damaging. They're associated with homocystinuria. It's when your homocysteine is not converted to methionine appropriately, and its level increased, and you can see it in your blood test, and it's a popular and important marker of cardiovascular diseases risk. And it can be corrected if there are some problems with imbalancing of methylation cycle disturbance. If you also will download the annotator for the drug interaction database, you will see that cyanocobalamin affects this gene. So usage of cyanocobalamin may help prevent the negative impacts of this gene variant. But then again, we should definitely check the blood level for that stuff, because genes are not that easy as we sometimes think. So the MTHFR gene, it encodes the enzyme which is called methionine synthase reductase, which enables MTHFR to turn homocysteine into methionine. But for this, we need enough B12 vitamin. If the enzyme activity is low, the risk of increasing of homocysteine level and cardiovascular diseases is increasing. Yeah, and polymorphism in these genes are associated with higher needs for vitamin B12 supplementation. So you should check your status of these vitamins to prevent some negative outcomes. And actually, folate metabolism genes are very popular in different commercial sets of analysis. You can see, and some of them are quite expensive. So they will just tell that we will reveal your folate metabolism or methylation, I don't know, status, etc. And actually, you can do it easily just by analyzing a few genes. You have a list of them, by uploading the filter and just looking to the information from the OpenCravat. Then what else we can analyze? We can analyze some genes related to neurotransmitters. For example, COMT gene, it's catechol aminotransferase, and the product of this gene, it affects noradrenaline and dopamine cleavage. So the product of this gene, it breaks down dopamine and noradrenaline. HTR2A, it's a receptor of serotonin. And you know, there are popular medicine like inhibitors of serotonin receptors and activators, etc. And DBH, dopamine beta hydroxylase. So when we're analyzing this gene, what does it affect? It affects our behavior genetics, like we can make some predictions about our motivation, etc. The most studied thing is risk of neurological disorders according to these gene variants. The need of supplementation, maybe magnesium, tryptophan, etc. And antidepressants usage. So actually, it's also related to pharmacogenetics testing. These polymorphism of these genes are related to changed response to some groups of antidepressants. Okay, so we can, again, go to OpenCravat, put these genes into the filter tab and analyze which variants do we have. I will do it now. I will send a list of genes. It's just actually 3 of them to our chat room. Oh, I'm sorry. I did it wrong. So just 3 of them. Okay. It's Anton's genome. We're just putting the variants and then see what we get. Mhm. Sometimes a table sign disappeared here, so you can just go to the Gene tab and choose View Table, and then it appeared. Okay, but when you're what I want to say, when you're analyzing some genes which are not related to any pathologies, you just want to know about some variants you get. You can just try to clear filters and just see what substitutions, which changes you have in that genes. So just without filters, just type and see what you get. So we can see plenty of changes in HTR2A gene, COM gene, etc., etc., etc. And then we can just look for the thing we are interested in from, for example, some scientific data, etc. Like we have, some interesting stuff from genetics. According to COM gene, it's like a warrior or warrior model. It's a gene variant that has been shown to predict the ability to maintain cognitive ability during competition, etc. I will try to find this gene variant. Wait. And according to that, you can make predictions on your stress response because people with one genetic variant, which has, okay. Quite a plenty of substitutions. So let's go back to the presentations. You see from Anton's genome, okay, slideshow mode. Okay, genotype that he got, GA genotype, it's valine to methionine substitution. If we have two alleles of methionine, it means low activity high dopamine. Allele carriers outperform like unchanged variant on a variety of cognitive tasks, because in like a normal state, we have high dopamine level, but it reverses under stress conditions, and homozygous change, which related to high dopamine and low stress resistance, high cognitive abilities, headaches may occur. And if we know that, we should not use precursors of neurotransmitters, etc. So what else we can do by using the OpenCravat? How to use in daily life with your genetic data. So you're just reading some interesting articles. Came across an interesting article. For example, there was one recently about leadership. So leadership, sample of bosses according to UK Biobank were analyzed, and they were found several variants which were associated with leadership phenotypes. With a focus on holding a leadership position and performing critical managing functions, etc. So you can find in this article this list of genes, a set of polymorphisms which are associated with this stuff, and you wanna find out whether you have some abilities to be to gain a leadership position or something like that. You can't find it if you have already done your genome sequence, because this article may just appear and you haven't this data yet in commercial analyzers. So you can just copy the gen list you want to analyze. Then again, go to your genome, put it into the filter tab, and okay, you have some kind of plenty of results here. And but anyway, you can analyze them and check it. So, but you also have here the RSIDs, which are or are not in this article. And having them from your article, you can just check whether you have these substitutions or not. So kind of that stuff. So maybe you're not having or having them, etc. So I have analyzed Anton's genome and have found that he has got several RSIDs related to these leadership genes, but just 2 of them. And if you find that you don't have any, you don't have to be upset, because it was observed that some positive genetic correlation between leadership position and some negative well-being indicators, including high levels of bipolar disorder, etc. So maybe the 2. I don't know why haven't I found it now? Definitely have been there. Okay, just I will check it one more time, but I was sure that it was there. I was checking it several times. So you can just put a list of genes, put a list of RSIDs you want to check, and then just check from some interesting article whether you have some interesting stuff from that or that you are not. So, and maybe one of the last genes, like some new information is always appearing in the literature. For example, CHRNA3 gene, it's related to smoking addiction. It's coding the nicotinic acetylcholine receptor, and several negative traits are associated with this gene. Nicotine dependence, cigarette consumption, smoking cessation, lung cancer, and some chronic diseases of lungs. So, and you want to just check, are you lucky to not have this variants, or you're not lucky and you have this variant? So you, as usually, you should just easily check this gene by putting it into the okay, we have to open. Return genes, just put a gene. Okay, apply filter. It's Anton's file. Yeah, file. Well, it's kind of slow. Until it analyzing, I will show on slides what we got. Okay, so we have found that Anton indeed is a carrier of some negative change that like this RSID, and indeed it was associated with this negative impact. So obviously he should not smoke. And you can easily check it on your own genome. And the last gene I want to talk about, you can also check it on transgenome. Okay, and I will briefly tell how to influence it, that gene. I will try to do it in our server because it's, I think it will be a little bit faster. So usually it's not that slow like now. We can use our preloaded filter. This is the gene we want to analyze. Apply it and see whether we have some negative substitutions or not. So you see that according to the OpenCravat, indeed it was found one variant of this gene which is homozygous, so it affects more severe, which predicted to be damaging in DLAT gene. And what does it mean? You can find some information from the detailed plan from the widgets of different annotators. Depends on how many annotators you have used. You can see that this gene encodes component of pyruvatic hydrogenase complex, etc. And you can find all of this information here and go to the links, etc. But I will briefly show you on the slides what does it mean and how can you just influence it. Okay, so then again, this gene is responsible of transport of pyruvate. This gene encodes an enzyme, E2 part of complex in pyruvate dehydrogenase complex. It's a part of a complex that plays an important role in the pathway that converts the energy from carbs into a form that cells into the form of ATP energy. So here you can see this complex which transports carbs to the mitochondria, and they will make energy for us in ATP form. Carbs and fats are the main energy sources for our cells, for our organism. And for carbs transporting into the mitochondria, responsible this pyruvate dehydrogenase complex. And if there are some problems with it, especially, for example, in this case, in E2 subunit. Okay, oh no, I haven't completed yet. Yes, it really depends on lipoic acid, so we should probably supplement it and check it into the level of it, etc. And if you are a carrier of such a variant, you may suffer for some weakness, for some faint when you get up, when you stand up quickly, you may feel dizzy due to this gene changing. So you should pay attention to balanced diet, to carbs and fats, etc., and maybe supplement with lipoic acid. But okay, individual genes are important for different stuff, but actually there are just a few genes which we can tell like confidently that they're indeed important, even if you find changes in these single genes, like top important genes. Genes are related with each other. They interact, they form gene nets. So if you wanna really discover whether this trait is about you or not, you should analyze like a whole set of your genes. And for doing that, we use polygenic risk scores. And I am happy to give talk to my colleague who will tell about polygenic risk scores.